Hi everyone. In the last set of notes, we introduced the square root parent function, and we talked about how the square root parent function and the quadratic parent function were related because they are inverses of each other. As long as you only take the positive square root function values, you get the square root parent function. That way you can ensure that your graph passes the vertical line test. So that was all kind of a quick review of what we talked about in our last set of notes. And in our set of notes today, we're going to talk about the transformations of the square root function. So in the past, when we've discussed transformations, we've talked about horizontal shifts left and right. We've talked about vertical shifting up and down. We've talked about reflecting over the x-axis. And then we've also discussed vertical stretches and compression. So we're going to talk about all of that again today with the square root parent function. And then we're also going to discuss the possibility that your reflection, instead of being over the x-axis, could also be over the y-axis. And we're going to talk about how instead of only vertically stretching or compressing, you could also take your graph and horizontally stretch or compress. So we're going to discuss those things as well. I feel like those last two things that I just mentioned are probably the harder things to wrap your mind around today. And so if you have questions, please make sure that you ask, because no question can get answered if it doesn't first get asked. So be vocal about what you need help with. So we're going to start out with the square root parent function. So here are the basic points that fit on most graphs. So we've got 0, 0, 1, 1, 4, 2, 9, 3. And the transformational form of f of x equals square root of x, it kind of mirrors what you've seen in the past. So you're going to have this minus h in here with x, which means that it's going to be under the radical and part of the radicand, because that's where x is located. So we're going to have x minus h in there. We're going to have plus k on the outside. That'll control the vertical shifting. We're going to have a on the outside, which will control vertical reflections over the x-axis, and it'll control vertical stretches and compressions. But the new thing that you're going to see today is this. And this b value is really important, and it can do a couple different things. And it is under the radical, so it's part of the radicand with x, which means that it's going to change things in the x form, which is going to be like horizontally. It's going to change things horizontally. So this is where you're going to see your horizontal reflections, so reflecting maybe from the right side to the left side over the y-axis. And this is also where you're going to see the horizontal stretches and compressions that we'll discuss in some of the later examples. So, in kind of a quick rundown of our normal transformations, if you horizontally translate or shift left or right, that means that you've either got a minus h, which moves to the right, you've got a plus h, which moves to the left. Remember, anything in parentheses, or really in general, anything with x, so that's going to include this b value in here. Anything with x is a lie. Spell anything right, Miss Belsick. Anything with x is a lie. So you do the opposite. If it says minus something, you shift to the right. If it says plus something, you shift to the left. The vertical translations come from this plus k on the outside. So if you have your square root of x plus a number, you move up. If you have minus a number, you move down. These are on the outside, so they're changing the y values vertically. We're moving up and down here. Now reflections. You've already seen where a is negative. And where a is negative, that's going to reflect over the x-axis in the typical way that we perform reflections, or we have performed reflections in the past. But now we have this added responsibility of determining if we have a negative inside with x, so under the radical with x. And if we have that, that's a horizontal change. And if it's a horizontal change and it's negative, that's a horizontal reflection. So it's taking anything that's opening one direction and it's moving it horizontally in this direction. So this direction would be the reflection over the y-axis. So you need to watch out for that because that's possible. The other thing that we want to talk about is the vertical stretching and compressing that you are familiar with. Sometimes it gives us a little bit of trouble, but in general, if you can see, if you move from the vertex 1 unit over and you count your units up, you should be able to get your vertical stretch value. So A is your vertical stretch or vertical compression value. If you have an A value that's bigger than 1, like 2 or 3 or 4, that's going to be a stretch because it's multiplying and making numbers bigger. If you have an A value that's between 0 and 1, so it's like a fraction in between there, then that's a compression and that's going to make your value smaller. Now we have this added responsibility again of the horizontal stretch and the horizontal compression. And this is kind of the weird part, because this horizontal stretch and compression is inside of the radical, so it's part of the radicand, and it's multiplied with x. And this doesn't really show up here, but I'm going to extend this and extend this, because this b value needs to be on the outside of the x, so it's got to have parentheses, and it's got to be on the outside of the x, but it's still got to be on the inside of the radical. So it's in kind of a strange situation. And because it is tied with x, and we said anything with x is a lie, because it's tied with x, then we've got some additional weirdness going on. So stretching typically means getting bigger. And in this case, because the horizontal stretch factor is inside of the radical with the x, then that means that it's a lie. And so anything that is small, so between 0 and 1, you typically think that you multiply by a small number, it makes things smaller, but in this case, it's going to horizontally stretch. In a similar sense, if your b value in here is bigger than 1, if it's a big number, typically you think, oh, that means stretching, but that's only if it's vertical. If it's horizontal in here with x, who's a liar, then anything that's a big number is actually going to horizontally compress your function. So it'll make a little bit more sense whenever we do some more examples, and when we get to problems that have these b values in here. So let's move on to the next page. Now, up at the top, because I don't want to have to keep switching or you to keep scrolling from first page to second page, I'm going to rewrite that transformational form that's at the top kind of under my table. I'm going to rewrite that up here so that I have it on my page. So f of x equals a times the square root of b times x minus h. This is where all the transformations occur inside of the equation. And when you do your transformations, it's likely that you'll have more than one transformation occurring in your equation at a time. And so this a and b and h and k value, those values have a particular order that you need to transform in. So you always use the b value if there is one other than 1. You use that first. Then you transform the h. So any x or any horizontal transformations will happen first, and then a and k, your vertical transformations will happen last. So this is the order if you are transforming that you need to transform in. So get my correct pen here. All right. It says, remember, when you graph, use the reciprocal of b for the scale change, or if you're writing an equation from a graph, you use the reciprocal for the scale change you found. And so this reciprocal that we're discussing, that means if you have like, I don't know, if you decide that the scale change is by 4, then you really use 1 over 4 because that's the reciprocal of 4. And so when we talk about scale changes horizontally, you're going to be using the reciprocal. That word is going to come up quite a bit. If the parent function f of x equals square root of x is changed in the following g of x functions, what transformations have taken place? And so in these two problems, we just need to list the transformations that have taken place. So I see a transformation here. Think about what that does. I see a transformation here. I see a transformation here. And I see a transformation here. So I see 4 different transformations that are occurring, 4 different ways that this function is different from the f of x parent function. So I don't see any b value change. There's nothing there. But I do see an h value change. This graph is going to be shifted 6 units to the what? If it's with x, it's a lie, so shift 6 to the left. If you have plus 6, that's shifting to the left. After you transform the h, you'd use the a, so that's right here. We've got 2 transformations embedded in that a value. One of them is a reflection over the what axis? It's over the x-axis. It's reflecting vertically, so perhaps it's up top and then you shift it below, so it's over the x-axis. Our typical reflections that we've done have been over the x-axis. This 1/2 right here, that's a vertical stretch or a vertical compression. That's a small number, so this is a vertical compression by a factor of 1/2. And then finally, we have the k value that we need to include in the transformation list, and that's out here. This is a -1, so how are we manipulating the function? Well, we are shifting down 1. So those are the transformations that occur. And most of your problems are going to be very similar to this. You're going to be asked to pick out the transformations that occur, or you're going to be given an equation and you're going to be asked to make the transformations on the graph. So in our next one, we have a transformation occurring here. We have a transformation occurring here. And we really have one here and here, but I'm going to erase that because it doesn't quite look like it's supposed to. It's supposed to look like something outside of a pair of parentheses with x minus h inside. It's not supposed to have a b value right here. It's supposed to be outside of parentheses. So in order to do that, I'm going to go ahead and divide by this coefficient right here. So what I end up getting is a 3 on the outside, like it was before, a square root, and then the radicand, actually the -1 comes out, kind of like a GCF here. Negative x over -1 is just x, which is good because we want it to just be an x at the beginning of the parentheses. And then 2 divided by -1 is -2. And then we have a +3 on the outside of the radical. So this better shows the pieces. I'm going to do this in, I think I had been doing these in pink because this is a b value and this is a little bit different. So we're going to do the b value first. We're going to talk about that change first. Now that change is a -1. The 1 really doesn't do anything, but the negative does. So if we have a negative in there for b, this is new information, so I'm going to go to my previous page. A negative indicates a reflection, and if it's inside of the radical, that means it's a reflection over the y-axis. So I'm going to go ahead and write that as my first transformation, that we have a reflection over the y-axis. I bet you could write the h transformation. We're using this, not this one, because this one wasn't in the right format. We need it to look like this. So what's the h transformation? It's a shift to the right 2 units. X minus 2 means shift right 2. The next transformation that we need to look at comes from the a value right here. That's a large number bigger than 1, so that means that we're going to vertically what? Stretch by a factor of 3. And then finally, our last transformation is a translation. It's the plus k out here. We have plus 3, so that is a shift up 3. Okay, so I'm going to move this down. These problems say if the parent function f of x equals square root of x, so that's the square root parent function, if it's changed in the following g of x functions, what transformations have taken place? So again, we need to identify the transformations that have taken place. I have one right here. And then again, I have this, but it's not in the right form. It needs to be something outside of parentheses and then x minus h inside the parentheses. So again, I need to take out this 4, kind of like a GCF. It's not exactly a GCF, but I still need to take it out. So this is going to be g of x equals the 3, the square root, the 4 that I'm taking out, and then 4x over 4 is x. And minus 1 over 4, that's minus 1/4. And even though I know we don't really care for fractions, it's okay. It's going to be fine. So let's talk about the 3 transformations that are happening here. And one of them happens to be weird. So we're going to transform with the b value first, because that's the order, b, h, a, k. This 4 is not negative, so it's not a reflection, but it is either going to be a horizontal stretch or compression. So I need to know that it's 4. Is 4 between 0 and 1, or is it bigger than 1? It's bigger than 1, and big numbers, when they're in there with x, that's a lie. That means they're going to make the graph smaller, so it's a horizontal compression. A horizontal compression. By a factor of not 4, but the reciprocal. So this is where our reciprocal language comes in. When you graph, or when you identify transformations on a graph, you use the reciprocal of b for the scale change. So if the b value in here was 4, then you use 1/4, because that's what really makes the numbers smaller. So we have a horizontal compression by a factor of 1/4. The next change we need to make is an h change, b, h, a, k. So this was the b change, now we need the h change. It's x minus 4, so we're going to shift right by just 1/4 of a unit. Very, very small amount. And then finally, we've got this change here. So this is the a value. Is it a vertical stretch or a vertical compression? It's a stretch since it's a large number, bigger than 1, by a factor of 3. Not the reciprocal, because it's not a lie, it's not in there with x. Okay, so I'd like for you to pause your video and try to come up with the list of transformations that occur in this problem. Check back for your answer. So this function g of x only has 2 transformations occurring. We have a minus outside, indicating a reflection over the x-axis, and then we have a minus 4 also on the outside, indicating a shift of the function down 4 units. So these are the transformations that occur. So I'm going to now move to my last page of notes today, where we are instructed to write the equation for the following square root functions and then give the domain and range. So not only do we write the equation, we have to give the domain, all the x's, and the range, all the y's. And we weren't told to use interval or inequality notation, so I'm going to go ahead and provide both because it is the notes. So in our first graph, our square root parent function, I'm going to go ahead and graph it on here in an alternate color, so in pink. Our square root parent function had points at 0, 0, 1, 1, 4, 2, and 9, 3. So 4, 5, 6, 7, 8, 9, 1, 2, 3. This was our parent function. So we want to know how the parent function was transformed to make this guy. Well, in order to transform it, take the vertex and figure out how it shifted. So this shifted 1, 2, 3, 4 units to the left. So 4 to the left. And once it went 4 to the left, we shifted 1, 2, 3, 4, 5 units up. 5 up. And this graph is not opening and rounding up. It's kind of opening and rounding down. So how would you suspect this has changed? Instead of curving up, it's curving down. So that's a reflection over the x-axis. Now finally, let's check to make sure that we don't have any kind of stretching going on. So remember when we checked for that in the quadratic functions, we checked to see how many you went up if you went over 1. Now this time, if I go over 1, then I go up 1, and that's where I'm supposed to be. So the same idea holds, over 1 up 1. So here, if I go down 1 and over 1, I land back on my graph, which is good. That means that there's no stretching or compressing that has happened. So this shift left 4 is an H change. This shift up 5 is a K change. And the reflection over the x-axis is an A change. So all of those are going to appear in our transformation format. So f of x equals a square root of b times x minus h plus k. So they're going to appear in there. Our equation will be f of x equals, the a value was a reflection over the x-axis, so it's a negative. There was no b value other than a 1 that's usually there. Our h value, if we shift left 4, then that's a plus 4. And then our k value was shifting up 5, so that's a plus 5. My domain is all the x values from here and over, because this continues on until forever. So this is negative 1, 2, 3, 4. And if it continues forever to infinity, we put an infinity symbol. We could also say that it's all the x values greater than or equal to negative 4. And then the range. It doesn't have a bottom boundary because we have this arrow, but it does have a top boundary at y equals 1, 2, 3, 4, 5. So the y values go from a negative infinity to 5. Or we could say all the y's are less than or equal to 5, which I kind of prefer that method. So this x boundary was at equals 5. Okay. Let's talk about the next one. The next one, if we want to decide where the parent function 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to decide where the parent function has translated to, you want to start from your vertex. We've shifted right 1 unit. We've shifted down 1, 2, 3, 4, 5, 6 units. So that's an H change and a K change. The graph is still going up and to the right, kind of rounding up. So there's no reflection that's happened. But let's count. Let's see. If you go to the right 1, you should be able to go up 1 and get back on your graph. But that doesn't happen here. We have to go to the right 1 and up how many? 2. So that means that this A value that we have here is 2, and that's a vertical stretch. by a factor of 2. So my equation, f of x equals, this vertical stretch is an a value, so I have a 2. There's no b value that I know of other than 1, so we're going to start out with x. If I shift to the right 1, that's minus 1 inside the radical, and if I go down 6, that's minus 6 outside of the radical. I find my boundaries, so my left boundary is at x equals 1. My right boundary, I don't have one because it goes on forever. So all the x values are greater than or equal to 1. My range has a bottom value at y equals 6, or sorry, negative 6. It goes up and up forever, so that's infinity. There is no top boundary. So we say all the y values are greater than or equal to negative 6. Okay. So what I'd like for you to do is pause your video and try this problem. Don't wait for me to show you everything. Try it out, and if you make a mistake, it's okay. Just fix it according to what you see in just a moment on my screen. All right. So I drew the parent function. The vertex shifts 5 units to the right and 3 units up. And instead of opening up and to the right, it opens up and to the left. So that's a reflection across the y-axis. That makes itself appear right here. The shift right 5 means minus 5, and the shift up 3 means plus 3. Now finally, I want to discuss this last one with you because it's a little strange. My graph has shifted from the vertex has shifted from the origin all the way here. So to the left, 1, 2, 3, 4, 5. So shift left 5. It hasn't shifted up or down at all. It's still opening up and to the right, so those are all good things. But I do notice that it is quite stretched. And instead of going to the right 1 and up 1, you've got to go quite a bit to the right before you can go up 1. Now it almost looks like it crosses here and here and here. If you can't tell, go with the point that's in the middle because that's most likely where it crosses. So instead of going to the right 1 and up 1, you have to go to the right 1, 2, 3, 4, 5, 6, 7, 8, 9 before you can go up 1. So this 9 is definitely creating this horizontal stretch, this pulling in this direction. And it's by a factor of not 9, but the reciprocal of 9. So that's a horizontal, abbreviated, horizontal stretch. I'm sorry, it is by a factor of 9. However, whenever this gets inserted into the function, because it's with the x plus 5 for the shifting left 5, it's in here with the x, so it's got to be a lie. So instead of using 9, I have to use the reciprocal of 9. So I have to use 1 over 9 for my equation. The domain is all the x values from negative 1, 2, 3, 4, 5 and to the right. So negative 5 to infinity, or x values greater than or equal to negative 5. And the range is all the y values from 0 up. So from 0 to infinity, or all the y values greater than or equal to 0. So in summary, we have a nice little set of examples for how to transform the square root parent function. And we have a lot of examples also of that new change, which is the b that occurs in here inside of the radical. And it changes horizontally, either stretching, compressing, or reflecting over the y-axis. So be careful for that.